So hello everyone, let's begin today's session with the contents of week 4. So in this week's course we have Norton Theorem, Compensation Theorem, Reciprocity Theorem, Maximum Power Transfer Theorem, concepts about independent sources and dependent sources, and we will again revisit old topic which is known as source transformation. So as we said in source transformation in the last week's course, we said that the source transformation is very important too, and the source transformation of Thevenin voltage and Thevenin impedance is basically the Norton current source and a Norton admittance or the Norton resistance. So similar to the Thevenin theorem, we said that if we have a black box and here we have some output resistance, let's say to be RL, we can represent this black box to be equivalent voltage source in series with the Thevenin resistance RTH. This equivalent voltage source we say it to be V Thevenin. Alright, and this output resistance RL is written here. So this black box is represented by a Thevenin voltage in series with a Thevenin resistance. Now applying source transformation to Thevenin's theorem, we are applying the source transformation. We can say that we can represent it as a current source in parallel with the same resistance, Thevenin resistance, which is also equals to the Norton resistance and the load. So thus comes our Norton theorem. So in similar lines with Thevenin theorem, we can say that any linear circuit containing several voltages or current sources and resistances can be represented by just one single current source in parallel with a single resistance connected across the load. Let's take this example again. So here we have, let's say, 12 volts and here we have 8 amperes. So this 12 volt and 12 ohms can be represented as source transformation. Let's say it to be 1 ampere. And parallel with the 12 ohm resistance, again we have another resistance of 8 ohms and we have another current source of 8 amps. So what we need to find is the voltage across this 8 ohms. So it can be found easily from here. So we can say, look, so in this is the reference node. In this node we are writing the KCL equation A. So we say 1 ampere is entering, 8 ampere is coming out, and V by 12 is coming out, minus V by 8 is also coming out, equals 0. V is the voltage at point A. So we have 7 plus V, this we get to be 12 into 8 by 20. So 5 by 24 equals 0. So we get V equals minus 7 into 24 by 5. So this much voltage. Alright, so this is the basics of the Norton theorem. So it has come from source transformation. So as we said in case of Thevenin theorem, we considered that if this is the black box and we removed the load, so after removing the load, whatever voltage comes across open circuit is the Thevenin voltage, and then considering all the voltage sources to be short and the current sources to be open, we have to compute the resistance across these terminals and we will get the Thevenin resistance. In similar terms, here also we have a black box. Here we will consider the short circuit current that is flowing when the terminals are shorted, and this is my Norton current IN, and again across these two terminals we will consider the resistance, equivalent resistance with the voltage sources shorted and the current sources opened up to get the Norton current, Norton resistance. So Norton resistance is equal to Thevenin resistance, and Thevenin voltage by the Thevenin resistance equals to the Norton current. This is the simple relation between Thevenin and Norton theorem. Okay. So next we have dependent and independent sources. So independent sources are those sources where the source value remains constant. Suppose we have a voltage source. Let's say we have a voltage source of, let's say, 5 volts. So no matter what current flows in or out of these terminals, the voltage across these two terminals will always be 5 volt, no matter what amount of current flows. Similarly, if we have a independent current source, which is, say, here 5 ampere, so 5 ampere will flow through the conductors, but the voltage across the current source can be anything. So the voltage across the current source V can be anything. Since these sources hold the quantities to be constant, like the current source has a constant of 5 ampere current no matter what is the voltage across it, and the voltage source has a constant voltage of 5 volt no matter what is the current flowing through it. These are known as independent sources because they are not dependent on any other quantity. Whereas so independent sources are usually represented by a circular symbol. If it's a voltage source, it is represented by a circular symbol with a plus and minus. So this is a independent voltage source, and then we have a independent current source, is represented by an arrow and a circular symbol. So this is an independent current source. In case of dependent sources, the source whose values depend upon another quantity, it mainly occurs when we try to model electronic circuits. So let's take an example of a current dependent voltage source. So dependent sources are represented by rhombus. So if it's a voltage source, it is again plus minus, and let it depend on some current I. So 2 into I is the voltage across this voltage source. So this is depend upon some current that is flowing, let's say in another circuit. Here some current is flowing I. So upon this current I, this voltage source is dependent. Similarly, there can be current dependent current source, current dependent voltage source, voltage dependent current source, voltage dependent voltage sources. All the dependent sources are represented by a rhombus. The other nomenclature remains the same. If it's a voltage source, it's represented by plus minus sign, and if it's a current source, it's represented by a arrow. So this is the basic difference between dependent and independent source. Our independent source has its value to be constant no matter what is the amount of change of the other quantity, but independent source is dependent upon another quantity, and hence they are represented using a rhombus, and independent sources are represented using a circular schematic. Next we have is the maximum power transfer theorem. So as we have studied the Thevenin theorem, so we can represent any circuit to be equal to a series voltage in series with a resistance. So now if the load resistance is now varied, what will happen? So the current flowing through this resistance will be I equals V Thevenin by R Thevenin plus RL. Right. So now what will be the power that is flowing through the load? The power that is flowing through the load is this voltage VAB into I. So power that is flowing through the load is VAB into I. That is equals to, what is VAB? By voltage divider rule we can get VAB to be V Thevenin by RTH plus RL into RL, and I is V Thevenin RTH plus RL. So here we have a square into RL. So if we plot the power to the load with the load resistance, we get this form of a curve. It rises up, reaches some maximum value, and then falls down to 0 again. The maximum power transfer occurs at when the load resistance equals to the Thevenin resistance. This we can also prove mathematically. How? Let's see. So we can take a derivative of the power with the load resistance RL. So we get VTH by RTH plus RL square plus RL VTH square by RTH plus RL cube minus 2 so we can write so this thing is equals to 0, so we can eliminate VTH by RTH plus RL whole square thing, and we will get 1 minus twice RL by RTH plus RL equals 0. So we get RTH minus RL equals 0. So the RL will be RTH under maximum power transfer. So from here we get that the maximum power transfer occurs when the load resistance is equals to RTH. So this is the maximum power transfer theorem. It states that if the load resistance is equal to the Thevenin resistance of the circuit, the maximum power will be transferred to the load. Now, instead of varying the load resistance, if we vary the Thevenin resistance by some means, so what will be the maximum power transfer? When will the maximum power transfer take place? When we vary the Thevenin resistance instead of the load resistance. It will be when the voltage is, then the RTH is 0. So when it is 0, the maximum voltage will come across the load resistance, and hence the power transfer will be maximum. So this is a trick question, please do keep in mind while solving the problems. So in maximum power transfer theorem, the load resistance varies, and hence when it's equals to Thevenin resistance, it will provide the maximum power to the load. But if instead of load resistance, if Thevenin resistance varies, it is at value of 0 of the Thevenin resistance that the maximum power will be transferred to the load. Next we have is the reciprocity theorem. Reciprocity theorem is a very simple theorem which states that the excitation and response can be interchanged, which means suppose we have such a circuit. This is the current I1 that is flowing through this branch, and this is the voltage V1. So suppose we have such a circuit, we can say that from reciprocity theorem that the excitation and the response can be interchanged in the form like this: R1, this is R3, this is R2. So here if we, in the place of response, that is I1, we place the excitation V1, we will get the I1 response. Similarly here, this is the basis of the reciprocity theorem, but we need to keep in mind it is not applicable everywhere. Reciprocity theorem is applicable only to single source networks. The network in which the reciprocity theorem is applied should be linear and bilateral. By bilateral I mean the current should flow in both directions, not in one direction, and the circuit should be linear. Linearity we have discussed in the last lecture. So the circuit should not have any time varying elements. All these parameters, the resistances, should not be time varying. Then only we can apply reciprocity theorem. So it's a very simple and very useful theorem. So that's it. That's the end of today's session. If you have any questions, please do let me know in the discussion forum. Thank you.